to all of you who have joined the webinar organized by Department of Mathematics, Pattamundai College, Pattamundai. Today, the Pattamundai College Mathematics Department of Mathematics is organizing a webinar on the topic Lattice and Algebraic System. The speaker of this webinar is Dr. Prayak Misra, PhD, who is currently professor in the Department of Mathematics and in the Silicon Institute of Technology, Bhubaneswar. I welcome Professor Prayak Prasad Misra to this institution, and as an introduction, I have to say that Pattamundai College is continuously organizing a blended mode of events like seminar and webinars in the college during the current pandemic period, and a part of this series, Department of Mathematics of this college, headed by Mr. Aravind Pandav, is organizing this webinar along with his colleague Dr. Nirmal Kumar Sahu. I now request head of the department, Mr. A. Pandav, to introduce our chief speaker of this webinar and also a few lines about the webinar. Mr. Pandav.
Thank you, Dr. Sunil Kumar Pradhan, IQC coordinator of Pattamundai College. So it is a auspicious occasion for the Department of Mathematics, Pattamundai College. Today, we are organizing a state level webinar on Lattice and Algebraic System. So before going to start this webinar, let me welcome our Honorable Principal, Professor Prabhakar Raut. In spite of his busy schedule, he was very much interested to join in this webinar due to some difficulties. Sari is unable to join here. In his schedule, we got some inspiration from our beloved principal. Now, the main attraction of this today's webinar, Professor Dr. Prayak Prasad Misra. Professor Misra is very much popular to our institution since a long. From 2008, we are conducting national level, state level, UG sponsored webinar. In each webinar, Professor Misra is always cooperating us. And regarding Professor Misra, he has served 21 years in the Silicon Institute of Technology, and he has completed his all the degrees of MSc, MPhil and PhD from Utpal University, Banibihar. And he is a man of mathematics and always busy in interacting with the students of that institution. All over the state, everyone knows him regarding his sincerity and belongingness to the students. I welcome sir to this auspicious occasion, to this webinar, that is Lattice and Algebraic System. Now over to Dr. Sunil Kumar Pradhan sir, who is the host of this webinar.
Thank you, Mr. Pandav, for your nice introduction. Now, as I am going through the introduction of Professor Misra, he has a long experience of 20 years of teaching experience and some large number of papers he has published in different national and international journals. I hope the webinar will be very much beneficial to our students, faculty members, and others who have joined this particular webinar. Now, I Once again, I welcome Professor Prayag Misra to this webinar, and I request Professor Misra to deliver his talk. Professor Misra.
Thank you. Thank you so much, sir, for these kind words. I hope I am properly audible to all of you. Can you all hear me?
Hello, yes, sir. Hello, Professor Misra.
Hello. Hello. Am I audible?
Your voice is not audible. Hello.
Hello.
Hello, Professor Misra.
Hello. Now am I audible? Am I audible now?
Now it is audible, sir.
Okay. Okay. Thank you. Thank you so much for inviting me and sharing some kind words for me. I will be delivering a talk. I think 45 minutes is given to assigned to me. So within this period, I will be sharing some slides and we'll discussing some problems on that area of lattice and algebraic system. I once again thank the principal sir and his team of Pattamundai College for inviting me to this webinar. So let me share my slides. Okay. I hope my slides are visible.
Yes, sir.
Okay. So the topic assigned to me is lattice and algebraic system. So I will be discussing, I will be starting with the concept of lattice first very quickly. Then I will come to the geometrical representation of this lattice. Then I'll come to algebraic system and I will link both of them. So to start with, to understand this lattice, give me just 1 minute time. Just a minute. There is a technical issue, just give me a few seconds. Okay. Now to understand this lattice, the concept of lattice comes from this Boolean algebra, where we need to go through a term called poset. To understand lattice, we need to know what is a poset. Poset means it's a partial ordered set. to understand this partial ordered set, we need to know what is a partial order relation. And this poset can be represented in the form of a diagram or hash diagram. I will be discussing all of these terms one by one. So that is why I'm writing this for putting a command over lattice, we need to know the poset and its representation in the form of a diagram called hash diagram. For understanding this poset, we need to know about partial order set and partial order relation. New marker. And to know more about this, to have a better culture on partial order relation, we need to understand the properties of relation. Which already we know, this is the basic. All of us know what is a binary relation. Basically, we speak about a binary relation R, which is from a set to another set, and this R can be represented as a subset of Cartesian product of any two sets. So this is the basic concept of binary relation. What is a binary relation? It is a subset of Cartesian product of any two sets. So when I am talking about this binary relation, it can be reflexive, can be symmetric, can be antisymmetric, can be transitive. All these are properties of a binary relation. So what about this partial order relation? Partial order relation is, it is a binary relation which is reflexive, antisymmetric, and transitive. As all of us know that to define this reflexive property, what we say, let R be a relation on a set A. I will take only one set A. So that means R should be a subset of Cartesian product of A with itself. So when I'm taking a subset of this relation becomes reflexive. This R becomes reflexive. It is a collection of all possible ordered pairs A comma A, such that this A should be for all A belongs to capital A. So we call, for example, if A is a set having 3 elements 1, 2, 3, then R becomes reflexive only when these 1, 1, 2, 2, 3, 3 ordered pairs are mandatory. We are not claiming that these are the only 3 ordered pairs should be present to make the relation reflexive. Rather, we are saying that these 3 ordered pairs are mandatory, are compulsory to be present in a relation to declare it reflexive. So we can, in addition to these 3, we can write some other ordered pairs also. Doesn't matter. But these 3 ordered pairs have to be present. Similarly, to make a relation symmetric, what we do? We say that if an ordered pair AB is present, then BA ordered pair has to be present. So if AB is available in the relation, if AB ordered pair is available, then BA ordered pair becomes mandatory. Then we call the relation is symmetric. Similarly, a relation is antisymmetric. When we call a relation is antisymmetric, if the relation is antisymmetric, means what? If in the relation an ordered pair AB belongs to R, if does not belong to I. AB is allowed, BA is not allowed unless A is equal to B. This is the definition we normally use for antisymmetry. Means in a relation, if you have an order pair AB, it is present, then BA has to be absent to make the relation antisymmetric. If at all BA is also present, then A has to be equal to B. Then we call the relation, binary relation, as antisymmetric. And similarly, this transitive property, we understand this transitive property in the form how if AB and BC both are available in the relation R, then A, this, comma, C has to be present. That becomes compulsory. So if both A, B, B, C are present, then AC is becoming compulsory to make the relation transitive. So basically, to understand this partial order set, we need to understand the Haas diagram. To understand this, we need to know partial order relation. To know partial order relation, we need to know all the properties of relation. So basically, the three properties are responsible to know this partial order relation. What are the three properties? The three properties are reflexive, antisymmetric, and transitive. So that is what is available in my next slide, that a binary relation R defined on a set A is called a partial order relation if the relation is reflexive, antisymmetric, and transitive. So these are the three properties mandatory for declaring a relation as partial order relation. So examples, I can take an example. The relation divides in the set of natural numbers can be a partial order relation because it is reflexive. I can say every natural number divides itself, so it is reflexive. All the natural numbers are dividing itself. It is antisymmetric because if a number, suppose let's say 2 divides 8, obviously 8 does not divide 2. So if A divides B, B does not divide A unless A is equal to B. So that is the property of antisymmetric, and it holds here. Then comes transitive property. If 2 divides 8, 8 divides 16. Obviously 2 divides 16. Means if A divides B and B divides C, obviously A divides C. Means C is divisible by A. Okay. So therefore, all these three properties of a partial order relation are satisfied here in the set of natural number under the binary relation divides. Hence, we can declare set of natural number, the relation divides in the set of natural number as a partial order relation. There are so many other partial order relations also. If I write set of natural number with, let's say, greater than equal to, this also can be a partial order relation. This greater than equal to relation is partial order because every natural number is greater than equal to itself is true. If A is greater than equal to 2, obviously B is not greater than equal to A unless A is equal to B. So therefore it is antisymmetric and it is also transitive. Hence, natural number under the relation greater than equal to is another example of partial order relation. I also can take natural number with less than equal to. Same logic, and this also is a partial order relation. So, I think Subraj Samal wants to say something. Raised hand, Subraj Samal. In between, if you want to speak, if you want to say something, you can interrupt me and you can ask your question or anything you want to discuss. Anyway, so these are the two additional examples of partial order relation. So we have understood the properties of a relation. I have reminded you. Then I told you the concept of partial ordered relation. Now I am going to partial ordered set, poset. Now this partial ordered set is what? A set along with a partial order relation. This one is a partial ordered set together, where greater than equal to is a partial order relation. But set natural number along with this relation together is called a partial ordered set. This is a partial ordered set. So what is a poset? Partial ordered set, or in short I can say poset. So this poset means what? It's a set in which a partial order relation can be defined. And that partial order relation means it is reflexive, antisymmetric, and transitive. So I hope all of you clear on the concept of partial order set. So therefore, when we are going to this partial ordered set, every poset can be represented in the form of a diagram. I can reflect the partial ordered set in the form of a diagram, and that diagram is called hash diagram. Hash diagram. So what is this hash diagram? Hash diagram is the geometrical representation of a partial ordered set. Okay, geometrically we can reflect a partial ordered set, and that geometrical representation is named as hash diagram. So how to draw a hash diagram? First, let us take a poset, a partial ordered set. Suppose let us take an example. Let's say I will take A is equal to say A, B, C, D, E. These are the 5 elements. Okay, and R is a relation defined on the set A, carrying the ordered pairs. Let's say A, B, B, C, C, D, D, E, E. To make it reflexive, because it has to be a partial order relation. So partial order relation means it is reflexive, antisymmetric, and transitive. So to make it reflexive, I have to write A, B, B, C, C, D, D, E. All the 5 elements must be related to itself. Then suppose A, comma B is there, B, comma C is there, C, comma E is there, D, comma E is there. Then A, comma D is also there. Then I will write A to C, B to E, and A to E. Now can you verify all these ordered pairs are present in the relation R? Can I announce, can I declare this R, this relation, as a reflexive, antisymmetric, and transitive relation here? It is reflexive because A, B, B, C, C, D, D, E, E are present. It is antisymmetric because AB is present, BA is absent. BA is not there. BC is present. Its opposite ordered pair is absent. So you can verify all that. Because antisymmetric says that if AB is present, BA has to be absent unless A is equal to B. Agar AB dono sahi mane equal hai, if they are equal, then only we can say AB, BA both can be present. Obviously they are not equal. These are all 5 distinct elements. They are different elements. Cardinality of this set is 5. So there is some alag alag hai. So obviously this is antisymmetric. Is it transitive? Because wherever ABBC is present, AB is present, BC is present. So SC has to be present. Yes, SC is present. So you can verify that if AB, BC is present, SC is present. Similarly, you can take AD. AD is present. DE is also present. AD is present. DE is present. So AE is supposed to be present, and yes, it is present. Okay. So in that way, similarly, AB is present, BE is present. So AE should be present. Yes, AE is present. Okay, AD is present, DE is present, so AE should be present. Obviously, it is there. So therefore, it also satisfies transitive property. So this relation is reflexive, antisymmetric, as well as transitive. Therefore, we can announce this relation R as a partial order relation. Okay, is it okay? So if this R is a partial order relation, then the set A along with this R together, A comma R, is what? It is a coset, partial ordered set. Because I said what is a coset? A coset is a set along with a partial order relation together is called a partial ordered set, coset. So here this is a coset, partial ordered set. As I said that every coset can be represented in the form of a diagram called hash diagram. So I also can imagine the hash diagram of this coset, A comma R. So when I will draw the hash diagram, so this is what I have written here, a set in which a partial order relation is defined is called a partial ordered set or coset. Okay. So here an example I have given, power set of a set under the relation subset. That is also a coset. How we will draw this? Suppose A is a set having 3 elements. Let's say ABC. Okay. And what will be the power set of this? Power set of these? All possible subsets. Curly bracket A, curly bracket B, curly bracket C, curly bracket AB, curly bracket BC, curly bracket AC, then ABC, and obviously 5. So these are the 8 elements present here in power set of A. So if I take this power set of A as a set and subset as a relation which is reflexive, antisymmetric and transitive, then together it is a coset. This is a partial order set. And I can draw the hash diagram of this coset. So that is what it says. The power set of a set under the relation subset together is called a partial ordered set. And its hash diagram is also possible. So we have taken 2 examples. First example I gave you this one. A is a set having 5 elements, and these are the ordered pairs present here, which is reflexive, antisymmetric, and transitive. I can draw a hash diagram of this one. Which one? This one, A comma R. Also, the second example says, if the set is A having 3 elements A, B, C, its power set will contain these 8 elements. So this power set along with the subset relation is also a partial ordered set, and its hash diagram is also possible. So how to draw hash diagram? So this example I have already given to you. This I have written here. So this A, B, B, C, C, D, D, E, E, then A, B, A, C, B, C, C, E, B, E, A, D, D, E, A. These are the ordered pairs. So when we are going to draw the hash diagram, in a diagram, in a graph, as you know in mathematics, graph contains what? Set of vertices and edges connecting any 2 adjacent vertex. So when you are drawing the diagram, hash diagram, we also follow the same principle. So suppose I just want to connect these elements. These are the A, B, C, D, E, 5 elements. So I have to make 5 vertices of a diagram. 5টা vertex 5 vertices. So when I draw, I will take A here, suppose this is A. Now A is, if you go back to the ordered pairs, A comma A is an ordered pair present in R. So I can make a loop here, A to A with an arrow. A is connecting to A. Then I have an ordered pair. This is already covered, A. Then I have an ordered pair A to B, A comma B. If I want to draw this is A, so this can be B. This is B, and there is an ordered pair B to B. So I can make a loop here, B to B. And A to B is connected, so an arrow from A towards B. Then I will come to B to C is there, yes. So B to C. With an arrow. B to C. Then C to C is also there. So there has to be a loop. There is a loop from C to C. Then I come from C to E is there. C comma E. So let us cover that part. From C to E. Again, E to E is there. So make a loop. You see, E to E is there. Then there is a connection from A to D. I will pick up from A to D. A to D. This is D. I have an ordered pair D to D also. Yes, D to D. That is covered. D to E, there is an ordered pair. D to E. With an arrow, D to E. What is left? A to C, B to E, A to E. These are the three ordered pairs. A, comma C, A to C, B to E, then A to E. So let us draw them. A to C, B to E, and A to E. Means now I have given justice to these ordered pairs. All the ordered pairs are captured here, where this A, B, C, D, E are the 5 vertices represented in the graph with the edges as ordered pairs. A is an edge, so A to A there is a loop. A B is an edge, so A to B there is a connection. Similarly, B to C. All those connections are made keeping these ordered pairs in mind. But this is not hash diagram. Hash diagram never says to draw a diagram of this type. This is just a general diagram, which any student, any school children also can do if you will make them understand. Hash diagram says that hash diagram is a very special diagram for whom? For the partial ordered sets only. So if you know that the set is a partial ordered set, it must be satisfying the reflexive property. So in the diagram, you need not have to make these loops. A loop kichi darkar nahi. It is understood that A, B, B, C, C, D, D, E, E have to be present. Otherwise, it is not recognized as a hash diagram. So we need not have to draw the loops in a hash diagram. What else we need not have to do? We need not have to put these arrow signs. Arrow sign kichi darkar nahi. Suppose there is an element A here, there is an element B above A, and A and B are connected. From here, you will understand that ordered pair AB is present in R, not BA. BA ordered pair is not present. Why not present? Because we will make an announcement that in this hash diagram, always the relation is from lower level to upper level. A to B, not B to A. means it is always in upward direction. That concept, suppose you will use in a hash diagram. You can use always the downward direction also. You can use towards left, you can use towards right. But in one principle, if you adopt that, suppose it is always upward, then no need to put these arrow signs. It is understood that it is upward related. Means the niche wala upar ke saath related hai. Ye understood hai. So you can, what are the things you can skip? You can avoid from this diagram to make a neat and clear hash diagram. That I am trying to make you understand. So you can avoid these loops. You can avoid these arrow signs. You also, why you are avoiding loops? Because it is by default reflexive. It is understood that loops are there, but they are hidden. It is understood that the relation is upward, so you are avoiding arrow signs. And the third point is, that is very important, that the third order pair of a transitive, because it satisfies transitive property. So if you have a relation from A to B and B to C, no need to connect A with C is not required. It is not at all required because it is understood. Otherwise, it is not a hash diagram. It is a hash diagram and it satisfies transitive property means, and A, B, C are connected means SC is understood. It is connected. So no need to draw A to C if A to B and B to C is already connected. Similarly, B to C, C to E is already connected. No need to connect B to E. Similarly, no need to connect A to E because A to C is understood. It is not connected directly, but it is understood because of A, B, B, C. And C to E is already drawn. So A to E you have to avoid. So in a hash diagram, if A, B, B, C are already connected, then AC has to be avoided. You have to skip A to C. So therefore, the hash diagram of this diagram is now what? Sorry. Just okay. So the hash diagram will be looking like this: A to B, B to C, C to E, A to E, A to D, D to E. This should be a straight line. It looks like, it does not look like a straight line. So you imagine that this is a straight line. I think there is some problem in the marker. Anyway, this is A, this is B, this is C, this is E, this is D. Now this is the hash diagram. Imagine that BC is a straight line. It looks like a curve, but it is a straight line. So now this is the real hash diagram of this example. Which example? This example. This is the hash diagram. So the hash diagram when we draw, we look at these three important properties. And what are those three important properties? They are reflexive, antisymmetric, and transitive. Must be satisfied. So to ensure that these three are satisfied, we need to avoid arrow signs and this what is that? Loop, and the third point is ordered pair S if A, B, B, C are already drawn. So in our next example, like I have given you one example of this set A is having three elements A, B, C, power set of a set along with subset. I want to draw the hash diagram of this one. So power set of the set A contains 8 elements. All the 8 elements are what? All possible 8 subset of this set A. So, and the relation is subset because all those subsets you have taken of capital A are reflexive, antisymmetric, and transitive. So therefore, this can be a partial order set. Now the hash diagram of this one will look like this. This is, here is the, it is phi. Phi सबसे नीचे रहेगा, सबुठु तळे phi रहबो. कहीं ना phi टा is by default subset of every set. So phi is of curly bracket A, phi is a subset of curly bracket B, phi is a subset of curly bracket C. Now A and B together are subset of AB. B and C are subset of BC. A and C are subset of AC. Now AB, AC and BC subset of ABC. Now this becomes the hash diagram of power set of A along with subset. This is the correct hash diagram. So in this way, we can claim that every partial order relation along with a set in which this relation is satisfied can be represented in the form of a diagram called hash diagram. Now, when you are drawing the hash diagram, you can find two important terms. What are they? They are called upper bound and lower bound. Okay. So this upper bound and lower bound of any two elements, you can decide, you can think, you can find out. You take any hash diagram, any percent. In every percent, you pick up any two elements, you can find out their upper bound. Now, what is that upper bound? Suppose I will take curly bracket A, curly bracket B. Upper bound means what? The element which is present above this curly bracket A and B, above. And both A and B should be connected to those elements. So that means curly bracket A and curly bracket B both are connected to AB and also connected to ABC indirectly. Okay, because of transitive property, we are not connecting directly. So what are the upper bound of curly bracket A, curly bracket B? They are AB and ABC. These are the two upper bounds. Now, out of these two, the upper bound which is present in the lowest position among all the upper bounds means this is an upper bound of AB and there is no upper bound between this and these two. इसके नीचे या तळको आउ upper bound नहीं कार A और B रो, then this upper bound is called least upper bound. So A and B has two upper bounds, AB and ABC, out of which AB is the least upper bound. If I will take B and BC, what are the upper bounds of B and BC? You will start with BC. BC itself is an upper bound of B and BC. Because B is related to BC, BC is also related to itself because of reflexive. So upper bound of B and BC is BC and ABC. Out of these two, the least upper bound is what? BC. So you will be able to find the upper bounds of any two elements in a hash diagram. Like this is a hash diagram. I want to find upper bounds. We have discussed this hash diagram before. Okay, this is a simple, neat hash diagram. And now in this diagram, I want to find upper bounds of B and D. Can anybody tell upper bounds of B and D in this diagram? What are the upper bounds of B and D? Any student? Can anybody answer? No? Are you there? My question is, there are two elements, B and D. I want to pick up these two elements and I want to find the upper bound of these two. Means what I have to find? I have to find an element to which both B and D are related. Can I take C as an upper bound? Can I take C? If you see the diagram, this B is related to C, but D is not related to C. So C cannot be an upper bound. Upper bound of B and D has to be E. This is the upper bound. Because B is related to E, D is related to E. Therefore, both of them have exactly one upper bound, that is E. If I take A and D, what are the upper bounds? I will start counting from D. D is an upper bound because A is related to D, D is also related to D. So D is an upper bound. Another upper bound is E. So upper bounds of A, D are D and E. What is the least upper bound? This one, D. Because among these two, this element is present below E. Below E. Therefore, D is called the least upper bound of A and D. So just like upper bound and least upper bound, you can find lower bounds and greatest lower bound. Lower bounds. We call it GLB. But in GLB, GLB is the greatest lower bound. GLB is the greatest lower bound. So among two lower bounds, like suppose I will take this example, the previous example, if I will take, I want to find lower bounds of SC and BC. Lower bounds, the element which are related to both SC and BC. So I can take C, I can take phi. These are the two elements which are related to both SC as well as BC. So the lower bounds of SC-BC are curly bracket C as well as phi. Out of these two, the greatest lower bound is C. Greatest. Okay. So when you are talking about least upper bound, you are considering the least element among all the upper bounds. When you are talking about the greatest lower bound, you are talking about the greatest element among all the lower bounds. Among all the lower bounds, the element which is present above is called greatest lower bounds. So in that logic, I can find greatest lower bound of C and D is A only. It cannot be B because B is related to C, but B is not related to D. A is related to both D as well as C. So it has only one greatest lower bound, that is A. Okay. So when you are talking about a lattice, the lattice is what? Lattice is a hash diagram, is a partial ordered set which has a unique least upper bound and a unique greatest lower bound. That partial ordered set is called a lattice. Means you take any two elements in the hash diagram, the LUB and GLB must be unique. Suppose let me take a hash diagram of this type. A set having 11 elements. I will take A as an element. This element is B. This element is C. This is D, E, F, G, H, I, J, K. One of the hash diagram I have drawn of a partial ordered set. Another hash diagram, that cube-like structure, I have already shown to you that partial ordered set. Let me just do it again. So this is phi, this is A, this is B, this is C, this is BC, this is AC, this upper one is ABC, and this one is AB. Now if you compare these two, these are two hash diagrams. but this one is a lattice. This one is not a lattice. Why? Because in this diagram, you pick up any two elements. They have a unique LUV, least upper bound, and a unique GLB, greatest lower bound. Meaning only one least upper bound and only one greatest lower bound of every two elements of this diagram. But here, you pick up F and G. Suppose I will take F and G. What are the upper bounds of F and G? H, I, J, K. There are 4 upper bounds. Among these 4 upper bounds, H and I are least upper bound, which is not unique. H and I are 2 upper bounds. So it is not unique here. Therefore, I cannot consider this diagram, although it is a partial ordered set, but it is not a lattice. So lattice means every two elements of the first diagram of the coset must have a unique least upper bound and a unique greatest lower bound, where this can be considered as a lattice. So this is the definition of a lattice. Lattice is what? It's a coset. Is called a lattice if every two elements of the partial order set have a unique least upper bound and a unique greatest lower bound. Unique means one and only one. But in this previous diagram, in this coset, the first coset, this cannot be considered as a lattice because there exist two elements, F and G, whose least upper bound is not unique. There are two least upper bound, H and I. So I cannot consider this as a lattice, I can consider this as a lattice. Algebraic system, every algebraic system can be connected with a lattice. So the understanding on lattice I told you, algebraic system, all of you know that, because when you are talking about a set along with some binary operations, together is called an algebraic system. So suppose operation and the relation, you know, this is all defined to relation. Reflexive, symmetry, transitive, everything. Operation means what? Mathematical operation, addition, multiplication, subtraction, means that operation can be defined in the form of a function. So if I take f is a function and it is a function from a cross a to a set, let's say B. Now this f, this function becomes an operation here. So the domain set of this function must be Cartesian product, means they must be present in the form of ordered pairs. Okay, and the range is another set, or it can be a cross a to a also, when this operation is closed. It is closure, it is satisfying closure property here. Here it is not closed. Okay, suppose in the set of natural number, addition is the operation. You take any two natural number, you add them. The result is of course a natural number. So therefore, we can consider this addition as a closure binary operation in the set of natural number. But in same set of natural number, subtraction may not be a closure binary operation. Because you pick up any two natural number, you cannot ensure that their subtraction will give you a natural number. If I take a smaller number first, 2 minus 5, that will give you minus 3. So minus 3 is an integer, not a natural number. So hence, this binary operation is closed here. Here it is not closed, but both of them are operations, binary operation. So if you have a set, and in the set you have defined a binary operation, now one or more binary operation, so together is called an algebraic system. So algebraic system and lattice, both the concepts you need to understand, then you can connect both of them. Means every lattice can be defined by an algebraic system or vice versa. Every algebraic system can be defined by a lattice. So when the algebraic system you want to define, that is what a set along with one or more binary operations defined on that set is called an algebraic system. Set of integers under addition, example. Okay, many more examples you can take. Set of natural number under addition. All that are algebraic systems. Real number under addition. Okay, then we come to some specific algebraic systems, which I think you people will be studying in modern algebra, like group, semi-group, monoid, all that, ring, integer. So those concepts are there. So when we are talking about algebraic system, we are thinking of a set with some binary operations. And I can connect a lattice that can be defined by an algebraic system. Means suppose, for example, set of natural number under less than equal to. This is a lattice. Already it is a tested lattice. The algebraic system defined by this lattice is what? It is the set of natural number, comma. The binary operation you are defining here, one is called named as join, another is named as meet. This one is called join, this one is called meet. These two operations are named like this. This is LUB, this is GLB. This is least upper bound, this is greatest lower bound. These are named as join and meet. So you can define these two operations from this relation less than equal to. Means when you are taking this less than equal to as a property of relation in this set of natural number, then this is reflexive, antisymmetric and transitive. Hence it is a post set, and in this post set every two element has a unique LUB and GLB. Hence it is a lattice. So for this lattice, the algebraic system responsible is natural number under join, comma, meet. So here you take any two elements, suppose 2 and 3. In this less than equal to, 2 will be present below, 3 will be present above, like this, 2 and 3. So 2, 3 ordered pairs should be present. Now what is LUB? What is the meaning of LUB here? If you take least upper bound of 2 and 3 in the diagram, 3 is the answer. So that means you are calculating maximum between two numbers. Here this means meet means it is minimum. So this join stands for maximum, meet stands for minimum. These are the two concepts we use here in this algebraic system for this lattice. So they are connected. They are connected. You take any two elements and you find out the connection between them. So any example, any other example, suppose I will say set of natural number under the relation divides. Obviously this is a lattice. Now the algebraic system defined by this lattice is what? Set of natural number under two operations join and meet. Now here what is the meaning of this operation join? Join means what? This relation is divides. Divides means when you draw the hash diagram, suppose 1 is here, 1 divides 2, 1 divides 3, 1 divides 4, 2 also divides 4. So 2 to 4 is connected in the hash diagram. 5, 1 divides 5, 6, 2 and 3 both divide 6. So obviously 1 divides 6. 7, 1 divides 7. Only 1, no other element. 7 is a prime number. 8, 1 divides 8, 2 divides 8, 4 also divides 8. So I can take a connection from 4 to 8. 9, 1 divides 9, 3 divides 9. No other elements divides 9. So from 3 to 9 you can make a connection. 10, 1 divides 10, 2 divides 10, 5 divides 10. No other elements divides 10. So 2 and 5 together can produce this 10 because 10 is divisible by 2 and 5. So 2 divides 10, 5 divides 10. So in this way, I can draw the hash diagram of this one. So if this is the hash diagram, what is the meaning of join here? If I take 2 elements, let's say 2 and 5, their join is 10 LUV. Their meet is 1. That means what? You take any other 2 elements, suppose 2 and 4. 2 and 4. Their join is what? 4. Their meet is what? 2. So that means what? I am calculating. Join means what? LCM, least common multiple. Meet means what? GCD or HCF, highest common factor or greatest common divisor. So this is the concept we use here for finding an appropriate algebraic system for this lattice. So this lattice is defined by this. This algebraic system can be defined by this lattice. So every lattice can be defined by an algebraic system, and every algebraic system can be defined by a lattice. They are interdependent. So from here you can start the concept of Boolean algebra. So anyway, I think it is already 1:28. So any question from your side? You want to ask anything to me? I will be happy to answer your queries. If you have to ask anything, please ask me. Any question from student side? Whatever I discussed, you want to know beyond this or something which you have not understood properly, you can ask me. Now it's over to your coordinator, sir. Lakshmikant. Yes. Okay, thank you so much.
Yes, ma'am. Thank you, Professor Mishra, for your nice presentation. For a last 1 hour and 15 minutes, we are listening to you, and some of the has actually passed over our head because we are not belongs to that of your department. But I hope this should be very beneficial to our students and faculty members who have joined to listen to you. Now, I request the faculty member of Mathematics Department, Dr. Nirmal Kumar Naik, to formally give vote of thanks. Dr. Naik. Sorry.
Thank you, Sunil sir. Esteemed Principal, Professor Prabhakar Raut sir, esteemed guest of honor, Dr. Prayag Prasad Mishra sir, and IQC coordinator, Dr. Sunil Pradhan sir, and respected head of the Department of Mathematics, Pandav sir, and other academicians join in this webinar, and our dear students. First, I would like to thank
our honorable principal sir for helping and encouraging us to arrange such type of a state level webinar based on the lattice and algebraic system. I like to express my deepest gratitude our research person, Dr. Prayag Prasad Mishra sir, who is professor in mathematics, Silicon Institute of Technology, Bhubaneswar, for delivering a beautiful lecture to our students and which is helpful in their future. And I would like to thank our head of the department, Pandava sir, to organize this webinar for our student. I would like thank to faculty member of various colleges attending this webinar and our student to listen this seminar. Last but not least, I would like to thank the technical staff of who are directly involved to help us to make this webinar successful. Thank you to all. Have a good day. Thank you. Now, the webinar is
now I request the participants to on their video so that a screenshot can be taken. All the participants should on their videos so that screenshot can be taken. Dear students, please on your videos so that screenshots can be taken. Nirmala